Welcome to this demonstration. I will showcase load balancing of VLLM AI inference model servers hosted in OpenShift, how this is different from regular load balancing, and how this is automated with OpenShift. Let's start describing the characteristics of load balancing AI inference servers. Regular HTTP workloads are fast, uniform, and cheap. On the other hand, LLM requests are slow, non-uniform, and really expensive, both computationally and economically because of the use of GPUs. Because of this, it is worth to spend cheap CPU to improve GPU efficiency via precise load balancing. LLM requests vary significantly in computational demands due to prompt length, the model differences, and previous outcomes, leading to unpredictable request running times. In this demonstration, it will be shown how F5 Big IP can perform intelligent load balancing based on the request body and the state metrics of the inference servers. This will be showcased using Big IP automation for Red Hat OpenShift and its integrated Prometheus telemetry. Let's see what is meant with intelligent load balancing in this context. When an AI LLM request reaches the Big IP, the very first thing that it will be done is applying a business logic. In this demo, this will be body-based routing. This is selecting the destination pool based on the content of the request. Once the pool is selected, in a second stage, the Big IP will select the most appropriate LLM server amongst the selected pool based on their metrics. These metrics are pulled by OpenShift Prometheus. Let's see in more detail the business logic. In this demo, the business logic used is body-based routing. This is in practice parsing the AI request, which is a JSON object, and selecting a pool based on its content. For this, we leverage Big IP's native JSON support. In this example, the elements highlighted in red will be evaluated. These are the model requested, if the request is an interactive application, or the role requested to the AI model. Next, it is represented a typical business logic as a diagram. Such logic diagram can be programmed in Big IP by means of using iRules, but in this demo, it is shown how to perform this without programming. This facilitates adapting to the business requirements swiftly and without requiring iRules knowledge. This is done by simply assigning an ID to each step of the diagram and specifying for each step the JSON element that we want to check, the value used to compare it with, and the next steps when the conditions are met or not. The resulting configuration is a data group with one entry for each step. This can be modified on the fly when business logic has new requirements. To see this in practice, next are sent 3 different batches of 10 AI requests that are routed to a different LLM pool according to its body and the business logic just shown. The second stage is about optimizing the VLLM servers of the pool selected in the first stage. To explain how this works, we start with a set of VLLM servers in a given pool. Using traditional load balancing methods, it is not possible to guess how busy are the servers, because unlike regular HTTP traffic, the responses are slow and non-uniform. To do a better servicing time, it is needed to gather the VLLM metrics, which include, amongst others, the request queue depth and request time, as well as metrics which allow to optimize VLLM's performance like the KV cache utilization. These metrics are gathered by OpenShift bundle Prometheus and Thanos telemetry packages. The metrics are then ingested by an LLM load controller that ultimately feedbacks these metrics as a load ratio to send more or less requests to each VLLM server. When the Big IP receives a request, uses this ratio setting updated every few seconds to bias the load balancing decision, ultimately improving the response times and optimizing hardware utilization. To see this in practice, we start sending requests to a model using round robin. Initially, the load is spread evenly, but eventually, because some VLLM servers get busier than others, receiving equal requests just makes things worse, and eventually, the load gets imbalanced, yet the same requests are sent to all VLLM servers. At this point, it is enabled dynamic load balancing, in which the metrics received by the VLLM servers are used to bias the load balancing decision. We can observe that the load is put back to an even distribution by continuously readjusting the ratios. This can be clearly seen when there is a spike. For more details how this demo has been created, please check the associated article. I hope you have enjoyed. Thanks for your attention.